Hello everyone, this is our last week of business statistics. In this week we want to deal with linear regression. So first of all, let me go to the lecture notes. Hopefully this brief review can help you to go over the material much faster. Let's take a look at the first part of the lecture notes. Um, so the linear regression is one part of the major applications of statistics. And we have simple linear regression, which involves only one independent variable, such as weather, and one dependent variable, such as um, how many cups of ice cream you can sell. Obviously, the temperature is higher, then generally speaking, the consumption or sales of ice cream should go up. And so that's why I'm saying the temperature is independent, and the ice cream sales essentially is the dependent variables. So in order for you to determine which one should be dependent and which one should be independent variable, then you have to think what is the economic arguments behind that. All right. And so let's go continue. Of course, regression analysis can involve like for the simple linear regression, yes, we involve is two variables, and yet you could have a multiple regression. That is, the ice cream consumption or sales can be influenced by not only by temperature, but also by maybe say the income or the population. Okay, so multiple variables could explain the sales of ice cream. So that's the philosophy behind the linear regression. Now, how to conduct this linear regression? Let's look at this simple linear regression model for a second. It simply says the dependent variable, which is represented by y, equals to a constant plus some kind of beta 1 times x. X in here is the independent variable such as temperature, and plus some kind of error terms. Epsilon represent random variable, which is essentially is error, because when you trying to estimate sales, you're always going to have some kind of error. Okay, and so this is the general model. All right, how to our task is actually how using the sample data, how to obtain beta 0 and also beta 1. If we using the sample, we can estimate a best value um, represent this data, beta 0 and beta 1, then we finish our task. The problem is when we do this kind of linear regression, just think of this. Okay, let's go to Excel using this as example. This is just an example from the lecture notes. If you look at the second part of the lecture notes, then you're going to see this data sets. Basically, it means that for each week, week 1 all the way to week 5, each week you have different type of TV ads per week, and then you're going to see the end result is how many cars actually has been sold. So this is the observations sample. All right, the TV ads has positive impact on car sales, generally speaking. But it's not exact one-to-one relationships. All right, so we know that it has positive relationships, but I don't know exactly what kind of relationship is. So we can basically do a scatter diagram. You can see this is number of ads, okay, on this side, the horizontal axis, and the vertical axis represent how many cars has been sold. So this is generally speaking the observations. So now we have 5 observations. Given these 5 observations, you can draw, if I want to draw the lines, you can draw many such kind of like lines trying to represent these relationships. All right, you can draw like this line, and you can draw another line. Let's say another line here, like this line. Okay, all these lines represent positive relationships. The question for linear regression is, what is the best line which can represent this relationships? Okay, is this line or the second line in this one? Okay, so we need to have some kind of criteria to determine which one is the best estimation. In other words, let's go back to this slides for a second. What is the best, based on this data, what is the best estimation in terms of beta 0 and beta 1 to represent this linear relationships? And so what is our criteria? It says that we could using this kind of criteria. We call this as the least square criteria. Okay, least square criteria. What does this least square criteria mean? Is the follows. Okay, if you notice this equation here, essentially just minimize the summation of the yi actually represent the true observations. In other words, yi represent, for example, if you place as for one time, you're going to see 14. All right, that's the actual observation. Then yi hat, yi hat essentially is estimated. Okay, given the model is correct, then what is your estimated value? Okay, in other words, okay, given this, if we suppose we already know beta 0 and beta 1, so what is your estimate? If this line is the line, let me get rid of this line first. If this line is the best representative of this data, and so if you have one ads per week, then you estimated cost sold should be sits right on this line, all right? But the true observation is either below this line or above this line. So if there's some kind of difference, in other words, let's go back to this equation just for a second. There's a difference in here, and this difference, we call this as error terms. Of course, you have a positive error, just like this observation. You see this one is above this line, you're going to have a positive estimation. In other words, you estimate it, you underestimate it. But this other observations, like this in here, you're going to have a negative error term. In other words, you overestimate the sales. All right, so you have positive error and a negative error, and so the principle behind this is that we want to sum all the errors together and want to minimize all these errors. If you can minimize all these errors, then you got the best estimation in terms of the models, beta 0 and beta 1. However, remember you have positive and negative errors. So in order for us to make sure that the negative and positive error does not cancel each other, so we typically want to square that error. So you notice this equation, you actually sum all these error terms together, right? And minimize all these terms. But you might ask me how to minimize this. You don't need to worry about this for a second. I can tell you that's good news, because Excel can automatically do this mathematical stuff and minimize all these error terms by providing you the best estimation in terms of beta 0 and beta 1. Right? So that's basically the principle behind this linear regression, and that should conclude